Welcome back to Mechanical Engineering Made Simple. Today, we are going to trace the entire life of a crucial machine component. We're going to follow it from a simple digital blueprint all the way to the tough, demanding reality of its working life, so we can really understand how the machines that power our world are actually built to last. I mean, think about it for a second. From the engine humming away in your car to the massive turbines generating our electricity, how on earth do these things withstand incredible forces, day in and day out, without just failing? Well, the secret, it turns out, lies in understanding the life of every single part inside. Okay, so to get our heads around this, let's zoom in and focus on one particular hero of the mechanical world, the rotating shaft. It's about as fundamental as you can get. Its whole job is to transmit power. And by following its story, we're going to uncover the core principles of strength, motion, and endurance that engineers have to master every single day. So where does it all begin? Well, every single component starts its life as just an idea, a blueprint. Long before any metal is ever cut, engineers have to be sure it has the basic, fundamental strength to survive. And this whole process starts with two key concepts you've probably heard of: stress and strain. First up is stress. The best way to think about this is to imagine you're in a tug of war. The force you feel in the rope pulling back against you, that's basically stress. It's the internal force that builds up inside a material to resist being pulled or pushed or twisted. It's really the component's way of fighting back and saying, nope, I'm not going to break. And what happens when there's all that stress? Well, you get strain. Go back to that rope. As you pull on it, it stretches just a tiny bit. That stretch, that's the strain. It's the physical change, the deformation that happens when you put something under a load. So you can think of it like this: stress is the cause and strain is the effect. Okay, so this is where the theory gets real, and engineers turn these ideas into actual concrete numbers. Our rotating shaft is getting hit with both bending forces, that's the M you see there, and twisting forces, or torsion, which is the T. So you might be looking at this and wondering, why are there two different formulas? Well, it's because materials can fail in different ways, and the right formula depends on the material you're using. For a steel shaft, which is what we call a ductile material, that distortion energy theory is usually the more accurate predictor. These equations are basically crystal balls. They let designers calculate the absolute maximum stress and then ensure the shaft is built strong enough with a healthy safety margin so it never even gets close to its breaking point. But look, just being strong isn't enough. Our shaft doesn't exist in a vacuum, right? It's got to spin smoothly while it's connected to all sorts of other parts. And that brings a whole new set of challenges. Things like friction, wear, and making sure nothing leaks. Let's see how engineers tackle these problems. To stop parts from literally grinding themselves into dust, you need lubricants. And this chart shows the two main ways they work. On one hand, you have hydrodynamic lubrication. Here, a thick film of oil completely separates the two surfaces. Think of a car hydroplaning on a wet road. It's the same idea. But if the pressure gets too high or the speed gets too low, that film can break down. That's when you get boundary lubrication, where just a microscopic chemical film, only a few molecules thick, is protecting the surfaces. Getting this choice right is absolutely critical. So to let our shaft actually rotate, it needs to sit in something called a bearing. But which one do you pick? As you can see, it's a real game of trade-offs. A classic ball bearing is fantastic when you're just starting up, but it will eventually wear out. On the other hand, a hydrodynamic bearing, if you keep it lubricated, can theoretically last forever and it's way quieter, but it takes more effort to get it spinning from a dead stop. The right choice here depends completely on what the machine is designed to do. All right, we've got our lubricants. Now we have to keep it in and keep all the dirt and gunk out. For that, we use seals. And the O-ring is just a perfect example of beautifully simple engineering. You start by just squeezing it into a little groove, which creates the initial seal. But here's where the magic happens. When the system pressure builds up, that pressure itself pushes the O-ring even tighter into the gap. So the higher the pressure gets, the stronger the seal becomes. It's just brilliant. Okay, so our shaft is now designed for strength and it's designed for smooth motion. It's perfect, in theory. But the real world is a violent place. The next phase of its life is all about surviving the intense, unpredictable forces that happen when the machine is actually running. And one of the most dangerous forces out there is shock. Now, this isn't just a big hit. It's a massive transfer of energy that happens in a tiny fraction of a second. It's that suddenness, that speed, that makes it so destructive and so incredibly hard for engineers to predict and measure. Now this is absolutely crucial. What you're seeing here are 3 different views of the exact same shock event, just measured with 3 different sensors. The high-frequency sensor at the top gives you the full, chaotic, hashy reality of what happened. But look what happens when you use lower-frequency sensors. They filter all that chaos out, and you get a much smoother, simpler-looking pulse. Now, if you're the engineer and you only see that bottom signal, you might think everything is fine, but you'd be missing the most damaging part of the impact, and you could end up designing a part that fails completely out of the blue. So, we've covered the design theory, and we've talked about the brutal forces of the real world. The final stage in our component's life, before it's ready for prime time, is this critical loop of designing, testing, and refining to make absolutely sure it's ready. This is the million-dollar question, isn't it? All those brilliant formulas and powerful computer models, at the end of the day, they're just predictions. So how do you bridge that gap between the clean, perfect digital world of a simulation and the messy, unforgiving physical world? Well, you start by admitting that your tools have limits. Computer models are amazing, but they are not crystal balls. The person running the simulation has to constantly ask tough questions, like, will my model even show me if this thing buckles? And just look at that last point. Vibration results from a computer model can have errors of 10 to 50%. You simply cannot trust the simulation alone. And this is exactly why physical testing is completely non-negotiable. You actually take the component and, you hit it with a special hammer to find its true natural frequencies, which you can then compare to your model. You stick it in an oven and then a freezer to see if extreme temperatures cause cracks that a computer would never, ever predict. Testing is where you find the ground truth. Okay, we did it. The component is designed for strength, for smooth motion, for shock. It's been tested, it's been refined. We're done, right? Well, not quite. All those vibrations we were just talking about have an annoying side effect that you can hear. That's right, the unwanted byproduct of all this powerful motion is noise. The good news is engineers have a whole toolkit for making machines quieter. They can use soft materials to absorb sound, put up barriers to isolate it, use special mounts to isolate the vibrations, or even add materials to dampen them. Of course, there are always mufflers. Most quiet designs are actually a clever combination of all these strategies. And for our rotating shaft, that number 4 on the list, vibration damping is absolutely paramount. And the best way to do that is to improve its dynamic balance. See, an unbalanced shaft is going to wobble as it spins, and that wobble creates vibrations that travel through the whole machine and radiate out as noise. A perfectly balanced shaft is a quiet shaft. So it turns out that good design for performance is also very often good design for making things quiet. So there you have it. We followed our component all the way from a set of equations on a screen to a fully realized, tested, and quiet part that's ready to go to work. We've seen how engineers have to constantly balance pure theory with messy reality and even deal with side effects like noise. This very process is what has built the entire world around us. And it really just leaves one question. As our materials get stronger and our machines get faster, what incredible new forces will the next generation of components have to endure?